Yeah, hello everyone. It's our pleasure to have Yu-Jie here to share about his work. Um, I think his work is particular interesting because he really shows we can do classifications on the state of matters using QCNNs and uh especially using some model in independent learning way that's is quite different compared to the previous proposals. And um UJ will be able to tell us more about that. And UJ, the floor is yours.
Uh, okay, thanks, Benya, for the kind introduction, and it's my pleasure to be here today. So, as mentioned, I'll be talking about this recent work with my colleagues about modern independent learning of quantum phases using QCNN. Before I start, I'd like to first acknowledge my collaborators. So this work was done in collaboration with Adam Smith, who was from a postdoc in our group, and now he's moved to Nottingham as an assistant professor, and Michael Knapp and Frank Pullman, who are professors in our group. So please, during the talk, feel free to interrupt me if you have any questions or you find anything that's unclear. Yeah, I think there's plenty of time. The talk won't be too long, I think. Good. So as we know, that in nature the matter occurs in different phases, and at zero temperature these are quantum phases of matter, which is a result of interactions between many microscopic particles inside the matter, and this has led to a variety of interesting phenomena, many body phenomena such as symmetry-breaking and universal scaling and topological invariance, and etc., which has been the central theme in the study of modern condensed matter, how to understand them and how to how do we capture them. And then, but there's still some significant challenges in this direction, and it's centralized around two keywords. One is the realization of these novel quantum phases of matter, and the second one is the detection of these novel quantum phases of matter. Now, in today's talk, I'm gonna center around the second keyword, which is the detection. So suppose now, yeah, I'm gonna center around the second keyword, and this is because with the development, we have the new development of this quantum science and technology now, and we have gained, have increasing control over many body systems. And one interesting direction is that people have been using these quantum platforms with programmability to actually realize these exotic quantum phases of matter. And then, but once these states are realized, for example, you can realize topologically all the states, you can realize all kind of exotic, many localized states on the quantum computers and all that. And then the question is, once you realize them, how do you detect the quantum phases? Or how do you know what you are preparing is exactly what you want? And this is the question that we wish to address today in the angle of quantum machine learning. Yeah, in the angle of quantum machine learning. Good. So in this talk, I'm going to primarily focus on one-dimensional gap quantum phases, but what I'm about to show can be straightforwardly generalized to high-dimensional quantum phases of matter, which I will mention a little bit of our recent exploration, but you can see that this is so one dimension is, as you will see, that one dimension would not be the limit for the method I'm about to describe. So in one dimension, quantum phases have been completely classified in a sense that given any gap local parent Hamiltonian, then you can, you can check the quantum phases of this system, and it belongs to one of the finite number of variable classes. And generically, there are three irreducible classes in these quantum phases in 1D. So one is called the symmetry-breaking phases, and an example of this ground state will be the GZ state. And the second one is so-called trivial states, and the example will be like the product states. The third one is so-called symmetry-protected topological phase, which is an exotic phases where there's no local way to detect disorder. Rather, in order to detect this disorder, you have to have some non-local order parameter. And this is precisely why it's called topological phases. But the presence of these phases requires protection from physical symmetries. And this has been done about 10 years ago to the classification of these phases. Now, our task is then very simple. It's the following. We want to ask the following question. So suppose now we are given some many-body ground states, which could be either solved by maybe quantum computers, or either solve it classically and prepare them on the quantum computers. In either way, so now we get some quantum states that is stored on your quantum platforms. And now we want to ask which known quantum phases of matter does it belong to? Okay, so that's the question we want to address. Now, as you see that this is different from on the classical computers, right? On classical computers, once we have the quantum states, we have the wave function, and we can basically compute everything using our classical computers. But on a quantum computer, this is different. We have realistic physical systems that encode in the ground states. Now, in an experiment, the traditional way of detecting quantum phases is to look for so-called the order parameters. So, for example, for symmetry breaking, what you do is you can measure some long-range order by finding the order parameters, the local order parameters, and you maybe take two of them, and then you measure this expectation value of the sky by taking them to be far away from each other. So that's one way. So for example, for SPT phase, symmetry protected topological phase, you have to take the so-called string order parameters, which is a non-local order parameter, and then this acts on larger and larger system size. Now, finding the correct order parameters first step, and then you have to measure them in an experiment to see whether the expectation value of this guy is 0 or not. Then from this, we can deduce the phases from the experiments. But however, as if you really dive into the variety of phases that you encounter in real world, and you realize that in fact finding the correct order parameter is not necessarily easy. Right? Finding correct order parameter that characterizes the phases that you're interested in is not necessarily easy. And secondly, even if you can find the correct order parameters, the order parameters are not necessarily easy to measure experimentally. Okay, so with these two reasons in mind, we can ask the following questions. Now, by by borrowing the technique from quantum machine learning, can we automate the discovery of the order parameters which correctly characterizes the phases of matter that we're interested in, and also at the same time, they are easy to measure experimentally, at least on a quantum computing platform. Okay? So this is the motivation. Now, in order to address this question, we can take a step back and go back to the theoretical understanding and ask ourselves, how do we classify quantum phases of matter in theory? And there's a very simple intuitive picture for doing so, which is shown here. So now suppose we have a ground state psi, and then we say that this ground state psi belongs to phase A if the ground state can be mapped to the fixed point of the phase by a finite depth local unitary quantum circuits that respect the symmetry of the system. Okay, so when I say fixed point, it means some kind of real space RG fixed point in the phase that has correlation length 0 for the gap quantum phases. Okay, and this physical picture is really nice and has been used to classify. Essentially, that's what was used to classify one-dimensional quantum phases of matter. And you can see that this relationship forms so-called equivalence relation. Then what you can do is you can group all the ground states of one-dimensional quantum systems into different equivalent classes. And these equivalent classes, they will correspond to distinct gap quantum phases of matter that are possible. Now, from this theoretical arguments, we can see that the necessary and sufficient information that we need to achieve quantum phase classification only contains two ingredients. One is a fixed point wave functions of the quantum phases. And the second one is a symmetry group of the system. Now, then once we know these are theoretically, the minimal ingredient we need for the classification of phases, therefore, in order to perform the quantum machine learning, we would expect these are also necessary and minimal information that we need. But it's not necessarily the sufficient information. But in this talk, I'm going to show you that indeed we propose a procedure such that these two guys are the minimal information and sufficient information we need for performing quantum phase classification using quantum machine learning. Good. Are there any questions so far? Good. Okay, let's proceed. So
why is the U minus
U minus?
U minus no, I minus, sorry. In your box statement.
Oh, sorry, this is a typo. I think this is an underscore, and then it's probably some formatting.
Okay, thank you.
Yeah. Sorry, thanks for pointing out. So the picture I had in mind is the following. So we want to perform now quantum machine learning, but as you see later, we're not performing quantum machine learning on classical data. We're performing quantum machine learning really on quantum data. So the scenario is the following. So once we have a quantum computer program which can actually distinguish the phases of matter, and in real world, you can, in the future, when we have actually working quantum computers, then it can be used to solve many of the ground states, even more complicated problems that's beyond the reach of classical computers. And then once you solve the ground states, you can feed it to this quantum computing program, and then, which is this robot here, and then it would tell you that, the input ground states belongs to maybe symmetry-breaking phase, triple phase, or symmetry-protected topological phase. Yeah. Now, in order to perform quantum machine learning, I need to choose a particular quantum circuit ansatz or architecture for performing such a task. And the answer I pick is so-called the quantum convolutional neural network QCNN. But I will mention at the end that in fact the method we propose is independent of quantum circuit ansatz, i.e. you can implement the method also to a variety of other quantum circuit ansatz. But here we are just choosing these for convenience because it has nice theoretical properties. So QCNN, as shown on the left-hand side, consists of three fundamental components. One is so-called a convolutional layer, which are these orange guys. So they are simply a finite depth quantum circuits acts on the bulk. And the second one is a pooling layer, and this guy consists of control rotation gates, which are controlled by subsets of qubits in the systems, and targeting in a data set the rest of the qubits in the system. And the qubits that are targeted would then enter the next level of a neural network, and these control qubits, they would never be touched throughout the rest of the network. And as you can see, as we enter the next network, this is similar to a coarse graining procedure, and then the same structure of the three of these pooling layer and convolution layer is repeated again. And you can do this multiple times until you are left with some finite number of qubits at the final level, and then there's a global unitary that acts on these qubits, and this layer is called a fully connected layer. So, not surprisingly, this QCNN has a very nice physical interpretation in terms of its architecture, which is mimicking the so-called coarse graining renormalization group flow. So you're basically taking a system and then you are shrinking the size of the system by doing some kind of RG flow. And secondly, there's an advantage of this QCNN, that is, you can see that these gates, they can in principle all be efficiently implemented on an actual quantum device, even though they are long range, but these only cause a polynomial complexity on an actual device. And eventually, if you want to measure the output of the QCNN, this means that it can be done very efficiently. Another interesting feature of this QCNN is that in order to perform quantum machine learning, eventually you want to optimize this QCNN from unknown parameters. And if you use gradient approach, you can show that the QCNN actually has no problem of so-called barren plateau, which is a ubiquitous issue in many other quantum circuit models. That is the issue when you are close to the global minimum of the of the cost function, then the gradient of this cost function would vanish exponentially in the size of the architecture. And indeed, this problem does not exist in the QCNN. And I'm just pointing out that also this has been actually implemented. Some simple example of this QCNN has been experimentally demonstrated on small systems. But however, despite all the nice features I just mentioned, the use of QCNNs so far the study of QCNNs so far only mostly concerned with analytical examples, where they can actually construct analytical solutions to QCNN. But if we want to train really QCNN using quantum data to really perform quantum machine learning, it still faces several challenges. And the main challenges are twofold. So one is that in order to train QCNN, we need a large amount of data in the form of the ground states of many-body system with the label of its phases. Now, this is very costly, especially within the foreseeable future, because we either have to solve this many-body ground state using quantum computers and feed it to the QCNN, or we have to solve it classically and prepare them on quantum computers. So either way, this is very costly to do. And second challenge is that if we solve all the data from some specific class of physical models, then these models can be highly biased, and therefore the trained QCNN can be very vulnerable and overfitted, because there may be some very fine-tuned features that's picked up by these QCNN. Now, in order to address this challenge, we propose the following simple protocol to train the QCNN, which simply consists of 3 steps. So suppose now you have several phases of interest that you want to detect. And then what we do is we randomly pick one of these, and then we'll prepare the fixed point of the phase on a quantum device. And then the second step, we apply a random local symmetric unitary gates on top of these fixed points. And then these randomly generated quantum state will be fed to the QCNN to perform a supervised machine learning training. Now, on the right-hand side, I'm showing the schematics of this procedure. So first, we prepare some fixed point wave function of the phase of interest, then apply a finite layers of random local symmetric unitary gates to the fixed points, and then apply the QCNN. And at the end, there are, in this case, 2 qubits left, for example. And suppose now I'm interested in the detection of 3 phases, such as the symmetry-breaking phase, the paramagnetic phase, which is a trivial phase I mentioned, and the SPT phase. Then I can assign 3 of the bit string labels to each one of these. So they correspond to somehow the probability or confidence score of these phases predicted by QCNN. And the 4th label can just be thrown away or considered as failure. So a subtlety that I will not go into too many details is that, of course, if you just do this procedure naively, you would actually fail. Okay, a subtlety is that you actually need to impose, apart from the physical symmetries in your system, you have to impose some additional spatial symmetries. For example, translation-invariants. And this is because that if you don't have these additional spatial symmetries, you can actually prove that the QCNN solution you're looking for actually does not exist. So this is a mathematical results which you can prove. And a physical picture of this is that suppose you don't have these spatial symmetries, then your perturbation could in principle be spatially independent, even though they're symmetric under the physical symmetries. Now, the spatially independent perturbation will be sufficient to scramble whatever information you have about the phases, such that there's no single physical observable can be used to pick up, to detect the phases that's within your system. Good. So with this in mind, that this simply means that when we apply this random local symmetric unitary perturbation, there has to, in our case, we'll impose a translation invariance on this thing to guarantee the existence of a solution. Good. Now, what are the advantages of this protocol? I mentioned this protocol, and the advantages will come from 3 points. The first thing is I mentioned before, as you see during the training, the QCNN only sees two things. One is a fixed point wave function. The other one is the symmetry of the system. I do not use any other information about these phases. So the training procedure is entirely independent of microscopic interactions or independent of any Hamiltonians in any way. Okay. And secondly, these fixed points wave functions, they are the fixed points of real space RG flow, which would have correlation length of 0. So as a result, they are typically, and in fact, generically, very easy to generate on quantum computers. For example, even for SPT, or even for higher dimensions, for these intrinsically topologically ordered phases, they are also very easy to generate because of just because they are the fixed points. So the third point is the most interesting point, that is this unitary perturbation applied to the fixed point. So there are two nice features of this unitary perturbation. That firstly, when you apply these random local symmetric unitary gates, what happens is that as you increase the number of layers, the average correlation length, as I mentioned, the fixed point has 0 correlation length, but as you apply increased number of layers of these random unitary gates, the average correlation length encoded in your input quantum data for the training can increase gradually as you increase the layers. Now, by doing this, you can train the QCNN starting from the data that has very short correlation length, which is easy to classify. Then, once the QCNN converges on this data, you can gradually increase the correlation length so that the detection becomes more difficult, but the QCNN becomes easier to converge. So by doing this gradually, then the convergence of the QCNN becomes much more stable and robust. And the second nice feature is that as you increase the correlation length on in your quantum data, these correlation lengths will wash out the microscopic details that's encoded in your choice of the fixed point, such that the QCNN will be forced to learn the long-range physics or the universal feature of the phase, but instead of focusing on these microscopic details. Good. Are there any questions so far?
Yeah, I do have one clarification. Maybe it's not really a question. So over here, like you have these advantages, and that means, okay, maybe you kind of mentioned this like before, but I somehow like kind of like miss it. But this basically, the first and third point basically means that your way of constructing the QCNNs is not prone to overfittings, right? Because like now you can basically classify different kind of like systems with the same like long range like physics. And I understand it correctly?
Yes. What was your question?
Not really a question, just like clarification. So like 1 and 3 basically just imply that your model wouldn't really like overfit
Yes.
the training data, right?
Yes, exactly. So especially as I mentioned, the feature 3, when we apply these random local symmetric unitary gates, it generates a finite correlation length in your data. And as you increase the correlation length, all the microscopic details, as these gates are random, all the microscopic details that's irrelevant for the phases will be washed away. And what's left is the long-range universal feature of these phases. So that's what will be picked up by the QCNN because of this random unitary perturbation.
Right. So like for fixed points, you have 0 correlation rings, and then you
Yes,
increase the
exactly.
Okay.
Exactly.
Okay.
Exactly. Good.
Thanks.
Cool. Yeah, feel free to interrupt me if you have any questions. Okay, good. So let's proceed. I've told you about the simple procedure that we can train this QCNN, but does it work? Right? So we have to do it on real physical examples, see whether that actually works. So I'm going to discuss an example on a one-dimensional example that is a systems with a time reversal symmetry, basically a one-dimensional system with a time reversal symmetry, which is generated by a global spin flip composed with a complex conjugation K. Now, under this time reversal symmetry, you can show the symmetry breaking as long as the symmetry is not, the spatial symmetry is not spontaneously broken, then there's only 3 possible phases under this time reversal symmetry. And one is the symmetry breaking phase, the other one is trivial phase, and the third one is the symmetry protective phases. And we can easily find fixed points phases, fixed point wave function for these three respective phases, which is simply the GZ states here and product states of pluses. And the third, the SPT phase is simply a cluster state which has a -1 eigenvalue under these Pauli strings act on 3 consecutive sites. Good. Now, once I prepare these, then the training procedure is that I randomly select one of these guys, and then I prepare them on an actual quantum device. And then on top of that, I will have to apply a symmetric 2-qubit perturbation in this case, and the 2-qubit perturbation is generated by this unitary generated by these Pauli strings. And these Pauli strings, you can select them such that this U commutes with the symmetry of the system, which is this anti-unitary Z2 symmetry. Now, as this is a schematic showing how this is done for example, for cluster states with 2 layers of U perturbation of U, and this cluster state can be easily prepared with the fine and depth unitary circuits exactly. Then you apply these 2 layers of noise, which consists of translation-invariant U. These parameters are chosen randomly for each layer. Then you apply the QCNN. Then you use the output to perform supervised training. Okay, good. So here I'm showing some of the results of the training. Then we can this is sufficient already. We know the symmetry, we know the fixed point ground states. Then we can actually go and perform training. Now, during the training, we have two different trials. So one is that on these first 2 parts, we showed the QCNN with different sizes. You can see it acts on either 4 qubits or either acts on 8 qubits. And in this case, the parameters, each unitary gate in the QCNN is independently parameterized. Okay, so they have independent parameters. And we optimize this QCNN for training. And the second case is that each parameter inside this QCNN has a translation invariance as well. So it's similar to the data. And then so that the number of parameters will be much less than the case of independently parameterized, in the independently parameterized case. And then we just test whether these 2 could both work. And in principle, you should expect them to both actually work out. Okay, good. So these are the results. So for each column here, I'm showing the number of layers we use, the number of layers of the noise we use during the training, basically the increased number of noise. And for each column here shows the number of layers of noise we use for testing, okay? And then these showing the percentage, basically the test accuracy of the trained QCNN. So as we can see, for example, for 4 qubits, we can increase this, but once we hit L is equal to 1 in the training, then the test accuracy basically saturates. It does not improve anymore. And if you go further, it could probably even decline. Okay. But once we increase to 8 qubits, then the test accuracy becomes perfect for small layers. And even as we increase layers in the training, it just slightly improves until it saturates on L is equal to 3, until it saturates after L is equal to 2, for example. Now, similarly, for the uniform case, you can see the test accuracy is pretty good, and then it somehow saturates more or less in L is equal to 2 during the training. And then these test accuracy are pretty high. And what's really nice, you can see when you test with only 1 layer of symmetric perturbation, which corresponds to data that with a very small correlation length, then the accuracy is actually perfect. Good. And we can see there's a physical interpretation why these are not perfect. Right? As we increase correlation length, the correlation length actually, when the correlation grows larger than the size of the QCNN, then the QCNN would no longer be able to detect correctly the phases of matter of the system. But when the correlation length is smaller than the size of the QCNN, then you should expect a very accurate prediction. Good. Now, once I train this QCNN from using this model-independent way, using the fixed point and symmetry, then since from this point on, the QCNN is trained and we will not touch them afterwards. Then we apply this QCNN to physical models that were not known by the QCNN during the training. Okay, this is what we're going to do next. So once we train a QCNN, we want to apply to some physical models we know which exhibit this distinct phases. So the first model we test on is so-called the cluster Ising model. So the model consists of three terms, which is this cluster term, and the second one is the ferromagnetic term, and the third one is a transverse view term. Now, by tuning the relative strength of these three parameters, you can actually reach three distinct phases that I mentioned before of the one-dimensional time-reversal symmetric system. And here is the phase diagram that we show. Here's the phase diagram of the system. The background color here indicates the theoretical phase diagram of the system, which we can solve either by analytics or by DMRG. And the color circles here then corresponds to the results of the QCNN prediction when we apply the trained QCNN to the ground states of the physical models. And you can see there are three distinct phases. One is the symmetry-breaking, SPT, and trivial phase. So when the colors of the circles match with the background color, it means the QCNN makes a correct prediction. If the colors mismatch, then it means the QCNN makes a false prediction. So now we're implementing the 4-qubit QCNN on this model. As you can see that when we go deeply inside the phase where the correlation length is small, the QCNN prediction is fairly accurate, but around the phase boundary, the QCNN prediction is less accurate, as we expect, because around the phase boundary, the correlation length is too large for the 4-qubit QCNN to accommodate. So we should not expect generically an accurate prediction. Now, of course, this model, if you stare at it carefully, this model can be mapped to a free fermion model using so-called Jordan-Wigner transformations. Now, what we can do is we can add a perturbation to this model such that it's no longer mappable to a free fermion chain. It becomes genuinely interacting. So this phase diagram is slightly shifted, but then we can again apply the QCNN to this interacting model, and we can see the prediction of the QCNN remains robust. And this shows that the QCNN is not fine-tuned to free fermion model. So far we're showing the 4-qubit QCNN, and it seems not to be ideal, but indeed we can increase the size for the QCNN from 4 to 8, as I've shown before. And now the QCNN has a larger system size and accommodates more correlation length. And you can see that the phase diagram predicted by the QCNN almost perfectly matches with theoretical phase diagram. Similarly to the interacting case. Now to see this more clearly, let's walk across this path, and I'm plotting the probabilities for each phase predicted by the QCNN along this path here. So these are the three lines plotted here. And the background colors here again indicates the theoretical phase diagram. You can see that the prediction of the QCNN is then made by selecting out the phase with the largest probability, and then the crossing of these largest probability will correspond exactly to where the phase transition happens. In this case, it coincides with accurately with the theoretical phase boundary. Good. So I've shown you on this very special model of cluster Ising model, which I forgot to mention. It has a very nice feature that if two of these three parameters are 0, then the ground states of the Hamiltonian, in fact, conveniently corresponds to the 3 fixed points of these three phases, which are these red dots. But we can also apply the same trained QCNN to other physical models, which is time-reversal symmetric, but it does not have these convenient properties that is continuously connected to the 3 fixed points we use. For example, I'm showing here 4 physical models that have that does not have these convenient properties. So here is the first model is this again this 1D model that has a cluster term, but now the transverse view term is replaced by a Y field, and the second one is again we have Y field here, but the cluster term in the middle is the X is replaced by Y. So in these two cases, you can show that indeed you can even analyze this system analytically because they are free fermion system. You can solve that indeed there's a phase transition at some parameter G, lambda is equal to half, And then on the left is SPT, on the right it's a trivial. And indeed, the QCNN correctly predicts these phases. And one interesting point is that you can show that these models, actually this model, is related to the cluster Ising model by a basis transformation. And now the QCNN is then accurate, can be able to predict the phases independent of the basis transformation, which is a feature that is not actually always true for conventional autoparameters. So it's the prediction of QCNN is actually robust. And what's more interesting is the third example here, and we can see that again we have a cluster-like term which is now x, y, x, and we have a y field. Now this model actually has a divergence of correlation length, and lambda is equal to 0. But this divergence of correlation length actually is a phase transition between two distinct quantum phases, but they are not protected by the time reversal symmetry as you show. It's protected by a different time reversal symmetry represented differently as different operators. But now, under this particular representation that we're interested in fact, these models belong to the same phase. It only belongs to different phase if we consider different time reversal symmetry. The QCNN is then able to actually tell this apart by saying, okay, this, even though there's a divergence of correlation length here, somehow for entire parameter, the phase is still trivial phase for this particular time reversal symmetry that we're considering. And the third example, the fourth example here is very different from these cluster-like terms. We can also walk away from these cluster-like terms and see that the prediction is still robust, and we can see the background colors here indicate the theoretical phase boundary. There's a symmetry-breaking phase. Actually, it's anti-ferromagnetic phase in the middle, and then there's two trivial phase again on two sides. Okay, so this physical example, we can see that trained QCNN is more robust than just predicting phases connected to the fixed point, but rather you can really characterize the phase in principle. Any ground states that's within the same phase. Good. Was there a question or?
Yeah, we do have a question from Daniel. Any idea why the probability assigned to the predicted phase is relatively small, around 0.4, even though the phase diagram are reproduced very well?
Oh, so you're basically saying why this guy is not perfectly one.
Yeah.
Okay. So this is because of finite size. I would say so. So this is only finite size, right? So it's a qubit. So for finite size system, quantum phases is never well defined. So quantum phases matter is, strictly speaking, only well defined when you take thermodynamic limit. So when you have finite size, there always some kind of, when you only have access to small system size, you can never be certain which phases of matter you actually, you can say, most likely in this phase, but you can always say this is what you're seeing is a finite size effect. Okay, so this is nicely reflected by the finite probability, less than 1 probability predicted by the QCNN. So in principle, if you increase the size of the QCNN, I would expect this predicted probability would then approach 1, and the rest of the probabilities will approach 0. And in the thermodynamic limit, you eventually have a perfect 1 here and perfect 0 for the other phases.
Okay, thanks.
Yeah, good.
Yeah, I do have another simple question, cross check of my understanding over here, because over here you say why the 4-qubit and 8-qubit example, the predictions they're so different is because of it's kind of the correlation length that it can distinguish, right?
Yes.
So if I compare for example 2 4-qubits QCNNs and then do some kind of ensemble learning, and versus the 8-qubit one, I still not be able to kind of beat the 8-qubit one, right? Because of the physics itself, it's just couldn't, even if I have two 4-qubit one, the correlation length is too large for it to detect. So okay,
yeah.
so do you get my point?
Not sure. Could you clarify a bit?
Yeah, so over here you compare one 4-qubit one,
Yeah.
QCNN, and one 8-qubit one, right? So
Yes.
now let's say we just do another kind of comparisons to compare 2 4-qubit QCNN, right? And then they add up to 8-qubit one, right? and then you train this like 4-qubit QCNN and
No.
trying to do some ensemble learning, I would expect this kind of scheme would fail as well because of the physics. Because even for 4-qubit QCNN, you couldn't really kind of like distinguish the phases with like long range correlations.
But,
And
yeah, but let me clarify that. So 2 4-qubit QCNN is not an 8-qubit QCNN, right? Because when I say 8-qubit QCNN, it's really the size of the Q. You can cross-grain level like this, and then it's not really the same.
So it's not really the same. So I'm just want to see, okay, say if I have 8-qubit device, like what is the difference if I like kind of like break it into 2 4-qubit device and then do some kind of machine learning trick like ensemble learning?
Yes.
Yeah,
You're right.
or just like use all of them to construct one QCNN. Like
Yes, exactly. That's exactly correct. Yes.
Okay, cool.
Yeah. I see. Thanks. Are there any other questions before we proceed? Good. Okay. Now, I've shown you that indeed the very heuristic method we propose, and not only works, but it works pretty well at these simple examples we've tested, and it works in a more robust way than conventional order parameters. Now, I'm going to discuss other aspects of this. So you can apart from this capturing accurate prediction of the phase diagrams, we know that in realistic quantum devices there always is noise. You can ask about, what about robustness, and what if there's noise happening? And to be honest, I don't have a full answer for this, but let me comment a bit on what happens when there's noise. Something you can prove, as I mentioned before, is a non-existent results. So suppose, let me state this slightly more clearly. Of course, this is not still the most rigorous way of saying it. You can check our manuscript if you want to see the most rigorous statement. But basically, if you have a system with a time versus symmetry, okay, then there exists no operators O that satisfy this condition. Basically, when you have ground state A, then O expectation value is greater than 0. When you have ground state B, then the ground state expectation value of O is smaller or equal to 0, such that O can be regarded as some kind of witnesses that distinguishes, or all the parameters that distinguishes phase A and phase B. Okay, so if there's only a time real symmetry, there's no other symmetry, then such an operator actually does not exist. So, but this proof is that it's a very simple use of invariance of so-called harm measure. But there's a very nice way. It's a very easy way we can simply circumvent this non-existent results, which is, as I mentioned, by imposing translational invariance in addition to the time versus symmetry. Then we can have, in principle, have a solution of this problem. But then we can see that the symmetry actually plays a crucial role in the solutions, even in the possibility of a solution in this quantum machine QCNN quantum machine learning problem. Then we can ask, in real device, of course, the symmetries are never perfectly satisfied. So we can have, the symmetry is definitely violated, but maybe to a small amount, or maybe to a slightly larger amount, right? Then we can ask, to what extent is the QCNN prediction robust against these symmetry violating small perturbations? And in fact, we can actually test heuristically that indeed for small symmetry violating noise, the prediction of the QCNN should be relatively robust up to a certain threshold. Okay, so one way to characterize this is by looking at so-called probability gap. So this would be the largest distance between the largest probability and the second largest probability. And we can sort of simulate the prediction as we increase the disorder, which slightly breaks the symmetry, translation-invariant symmetry in the system. And then you can see how long does it take, what's the strength does it take for these, for the probability gap to vanish, which is the point where the QCNN stops being able to distinguish unambiguously the phases of the system. And you can see that there indeed is a finite distance, but this is a finite size effect, of course. Whether this holds true for thermodynamic limits is actually a very interesting question that we should be investigating in the future. Now, another question we can ask is that you can say, look, this QCNN seems to be nice in one dimensions. It can detect faces, but you have to know something about the faces. You have to know how many faces are there. What are the possible faces out there? What about unknown faces? Can we use this to detect faces that we do not know about? Of course, this question, I don't have a full answer, but an interesting experiment we did was that to apply the trained QCNN now to a model where the phase is not known to the QCNN, is not input in the training. So basically, we train with phase A and B, but then there's a third phase C that was not included in the training. Then we apply the trained QCNN based on phase A and B to some ground states, which is in phase C. So now this is the probabilities for each phases. You can see on the left-hand side here is some kind of SPT phase, more or less the QCNN knows about. But then on the right-hand side is a phase C that the QCNN does not know about at all during the training. There's no label for that. And you can see that what happens is that on this side, the QCNN knows with confidence that we are in some kind of SPT phase. But as we go across this SPT phase into some unknown phases, what happens is that the QCNN gets confused. So basically, the probabilities for each phases becomes comparable to each other. So now it becomes harder. You just don't know which phase does it belong to. Okay. So this might suggest that we can actually improve this QCNN by incorporating so-called the technique of confusion learning. And then by doing this, you may be able to go one step beyond what I have already shown you, that to detect phases that are unknown actually before we perform the training. Good. And another interesting point is that you can argue to me that I've shown all the results showing you so far focus primarily on one-dimensional systems. You can argue, okay, in one dimension, core it's very core, but then in principle, we have understood everything about one dimensions. It's relatively easy to simulate, and then there's no physics that we don't know about. But of course, as I mentioned at the beginning, that this method, although we focus on 1D, can be easily generalized to high dimensions. So this is an attempt that we made recently. It's work in progress, so I cannot give too many details, but roughly goes as follows. So for example, we can actually apply the method I mentioned to intrinsic topological order in 2 dimensions, for example. An example of this is so-called a toric model, which with a Z2 topological order. And we can consider a phase diagram that looks like this. For example, there's a toric phase here, and then on top of the toric Hamiltonian, we add some transverse field along the x direction and along the z direction. And as we add the transverse field, there's a topological phase transition from the toric to some kind of trivial phase, which is adiabatically connected to product states. And sometimes people call this Higgs phase and confining phase because it's in relation to Z2 gauge theory. Now, what I can do is that I can take the fixed point of this Z2 topological order, which is the toric code, and then I take another product states, which is, I should put this red dot far away, infinitely away from along this axis. Take one of the product state and then apply the training procedure I described before. Now then I apply the trained QCNN to the ground states of this phase diagram to make prediction. And you can see that even for intrinsic topologically ordered phases, the phase diagram was again accurately reconstructed by the QCNN. And you can see that what's even more interesting is that there's an EM duality in this phase diagram. That is the reflectional symmetry along this axis. That is the X and Z somehow are the same in the toric code. Now in the training, initially we only feed one of the product states, but somehow the EM duality re-emerges approximately as the QCNN makes prediction. So indeed, there's a hope that it can actually work in high dimensions. And there, it might be able to teach us something new. With this, I would like to conclude my talk. So in summary, I've shown you that there's a very simple procedure that we can generate a large amount of quantum data for training using only the information of fixed point wave functions and symmetry, and we can perform model-independent training to detect quantum phases of matter using QCNN. And secondly, I point out the importance of symmetry. So symmetry consideration seems to impact even the existence of solutions severely, and then so it's important to understand the role of symmetry in and quantum machine learning. And the third one is the potential generalization to high dimensional phases. One is the toric code I mentioned, the intrinsic topological order I mentioned last slide. And more recently, we have work which shows you can actually physically realize topological phase transitions in 2 dimensions. So this has give us a platform, but these are so-called symmetry-rich topological phase. So this gives us a platform to actually probe the properties across this phase transition. So it's very interesting to combine these experimentally realizable examples with the QCNN in high dimensions to see whether it actually works. Because simulation of this thing is actually very difficult on classical computers when we go beyond 1 dimension. So it'd be good to actually do this on an actual quantum hardware. Okay, so that'll be the end of my talk, and thanks for listening.
Cool. Thanks, Yu-Jie, for a very interesting talk, and yeah, the flow is very clear. And especially is how you kind of explain the physics and how everything's are related to each other's. It's very easy to follow. So for the audience, if you have any questions, then feel free to unmute yourself and ask the questions, or you can type the questions in the chat and I could have you ask. Meanwhile, I could ask one simple questions. Are you aware of geometric quantum machine learning, this field?
Can you describe a bit what it is?
Yeah, so recently there's one new directions in quantum machine learning, basically trying to incorporate the symmetry, to basically understand how you can design your ansatz by utilizing the symmetries of your data. So over here you have quantum data, then these quantum data respect translational invariants or whatever, or rotational invariants, for example.
Yeah.
Then this geometric quantum machine learning give you a way to utilize this symmetry and systematically construct the ansatz, your quantum circuit based on this symmetry. Yeah.
So it's equivariant quantum circuit ansatz, right? So that's what's
Yeah.
Yeah, and yeah, I'm aware of those. There's quite a few works on this thing. Yes, exactly. That's actually a very interesting topic to be explored in this context of QCNN, because the symmetry they were considering in most of these works, I wouldn't necessarily call them quantum, right? Because most of the symmetry they consider are very geometric, as you mentioned. It's either translation invariance or permutation invariant, or some kind of these physical geometric invariants. But in quantum setup, an interesting question you can ask is can we incorporate the symmetry of the system to the symmetry of the system to the quantum to the QCNN, and the symmetry in this case would not be simply some classical symmetry, but rather as quantum symmetries, which has a non-trivial maybe Hilbert space and computational relations. For example, you have Z2 cross Z2 or anything like this, which is protecting the phases that you're interested in. This I don't know how to do, and I'm not aware that any works that could actually do this in a very meaningful way. But that's only to the best of my knowledge.
Right. I think I didn't follow this line of research that much, but I think there are some work trying to utilize the symmetry in quantum data, like quantum symmetry, to construct the ansatz. But yeah, I think we probably have to kind of read more in order to see the differences between your work and theirs. Yeah, and because over here you kind of do everything in very physical perspective, right? And currently a lot of people is trying to characterize some kind of generalization errors or our distribution generalization errors, and it's from a kind of pure machine learning perspective, basically trying to use machine learning tools to do the analysis. For example, how the expressivities, how complicated your model, your QCNN is, and how trainable it is, brand plateaus and generalization errors. So over here it seems a very interesting perspective is to go from a pure machine learning perspective and understand how why your model can generalize to other models, because what we call our distribution generalization is that we sample the training data from one distribution, train our models, and then now we use our model to to basically predict on testing data that sample from the distributions there's
Mhm.
not the similar distribution of your like training distribution. It's like very similar to what you have done here, train
Mhm.
using like one particular systems and then trying to make the predictions on other systems. So
Mhm.
it's kind of interesting to see like how we can combine these two frameworks and trying to kind of find the machine learning theoretical machine learning way to quantify the performance of your model.
Yeah, exactly. That would be very interesting. Yes, I try to think about this, but my knowledge on this learning theory is not enough yet to do this. But it'll be
Yeah,
interesting.
so I
Future.
think it's like you could, I don't know, as an okay for those anonymous people, like those guys who propose geometric quantum machine learning, they have a lot of kind of like their expertise is of course on bare metals, the trainabilities, but I think they also like kind of do some generalizations error. But so it'll be kind of interesting to see how like these two can connect to each other. I
Yeah.
don't know. Yeah.
Yeah, I think it's a well-defined problem. So basically,
Yeah.
here I have a very well-defined distribution of data for training, and then there's a well-defined answer. So I think it's very plausible that you can prove certain generalization bounds for this model, as long as you can define. You may be able to find a mathematical way to define this distribution of data sets more conveniently. But once you do that, then you can probably prove some generalization bounds for this QCNN model I just mentioned. Yes, I think this is actually something interesting to explore. Yeah.
Yeah, just curious. Okay, I think I might have like missed the explanations about it. So for others, like for your testing model, right? Like for those that are not the one that you use for training, like are those like are those models also generate in the same way? You find some like fixed point states and then apply the symmetries, or yeah, you kind of like do some renormalizations and
I
trying
mean,
to find
these guys?
yeah, this guy.
No, these guys just take the Hamiltonian and solve the ground states.
Okay, so you are not using the similar
No,
ways.
so all these guys, all the testing I show is using the actual ground states solved from a physical Hamiltonians.
Mhm.
And as I mentioned, during training, you don't see these
Yeah.
anything. But then when we test them, we have to, test it on physical models. And these are exactly the ground states solved from these Hamiltonian. And then we feed the ground state to QCNN for it to test.
Right. Yeah, because I was just thinking, trying to exploit some common properties, in terms of the state symmetries. Oh, sorry, like the state, the initial state, like the initial starting point, and then trying to prove that generalization bound. But maybe this is just like too kind of simple of a thought. Maybe like need to think more of how to kind of like develop the generalization bound for this kind of models.
Yeah. It's a well-defined problem, but it's not obvious how to do this.
Yeah, because like there's one like good like very recent work, like I think first ever like our distribution generalization error bounds. They're just like trying to explore the properties of Haar randomness. Like you can train your models using some local Haar random like local Haar kind of like random states, and then it's like you can make the similar predictions on the global Haar one. Actually, you can define our distribution generalization error that way. So there's kind of common properties of the like training and testing state that you can exploit and develop our generalization distributions.
I see.
Yeah, that's why I asked that questions whether there's a common kind of state that you train. But since you are training from testing everything's like by solving the Hamiltonian, so it might.
Yeah, but then I train and test on the same thing. From this
Okay.
table. Then this is the number of layers of noise I apply during the training. Then this are the number of layers of noise I apply in the testing. So in this table, then I train and test on the same distribution of data.
Okay. Right.
This is only for benchmarking the training procedure. So I know when these converge, for example, right? And then this is exactly the accuracy that you can get for these.
Right.
Now, but the testing data is then artificially generated by random perturbation. In the later slides, the examples I showed then is testing on completely different things, which are ground states generated by physical models. But in the training, I can already test the model, but with the same source of data
Right.
Same way of generating the data, and these are shown on this table here.
Right. Oh, and I remember you mentioned that there's one model that is just different by a basis transformations. Like which one is that?
So this model, no, this model is by basis transformation relating to this model. When one of the coupling is 0.
Okay.
Yeah.
Okay, I think I just have to go and study in depth of what's the common properties of these physical systems and
Yeah,
yeah.
these are physics, so you can
Yeah. Okay. Yeah, I think so now it's 5:04, so I guess we could probably end the seminar now. And yeah, so for the audience, if you have any questions, I think you can just like contact Yu-Jie and ask about that. And yeah, thanks Yu-Jie for the very interesting talk, and hope to see you again in our seminar.
Thanks.
Yep, see you. Bye.
Thanks for listening.